In this lesson, we will delve into the principles and equipment of laser processing technology within the special processing techniques covered in Project 2. As a crucial component of special processing, laser processing technology overcomes the limitations of traditional cutting methods, enabling tasks such as soft overcoming hard and bladeless cutting, which are unattainable with conventional machining. Next, we will explore in detail the principles, characteristics, equipment, and practical applications of laser processing, allowing us to experience the allure of this innovative technology. In the field of metal cutting, traditional machining methods often rely on direct contact between the tool and the workpiece using mechanical force to remove material. However, with the advancement of industry, the demand for processing special materials and complex shapes has been increasing, making traditional methods increasingly inadequate. It is in this context that special processing techniques have emerged, with laser processing technology standing out as a prominent example. Laser is a beam of light characterized by high energy, high directionality, and high monochromaticity. The principle of laser processing is based on the high energy density of the laser. When the laser beam is focused on the surface of a workpiece, its energy is highly concentrated, causing the irradiated material to rapidly heat up to its melting point or even boiling point. This results in phenomena such as melting and vaporization of the material, thereby enabling operations such as material removal, drawing, and modification. From a physics perspective, the interaction between laser and material involves complex energy conversion processes. The energy of the laser is transferred in the form of photons to the atoms and molecules within the material, intensifying their thermal motion and causing the material's temperature to rise. This process can be explained by the law of conservation of energy. Assuming the energy of the laser is E laser, the energy absorbed by the material is E absorbed, and the energy lost is E lost. Then we have E laser equals E absorbed plus E lost. The energy absorbed by the material is used for melting and vaporizing the material, while the lost energy is primarily dissipated into the surrounding environment through heat conduction and thermal radiation. I energy density. The laser beam can be focused into a very small spot with energy highly concentrated, allowing it to process various high hardness and high melting point materials, such as ceramics and diamonds. This exemplifies the characteristic of soft overcoming hard. Although the laser appears intangible, it can easily process hard materials that are difficult for traditional tools to handle. 2. Non-contact processing. During laser processing, the laser beam does not directly contact the workpiece, and there is no mechanical force involved. Therefore, issues such as tool wear and workpiece deformation caused by cutting forces do not occur. This is known as bladeless cutting, overcoming the limitations of tools in traditional machining. 3. High processing precision. The focused laser spot can be as small as 10 to 30 micrometers, with an economical processing precision of plus or -10 micrometers. Nanometer level processes such as extreme ultraviolet lithography belong to specialized fields and are not within the scope of conventional laser processing. 4. Great processing flexibility. Laser processing allows for precise control of the processing procedure by adjusting parameters of the laser beam, such as power, pulse, width, and frequency. This adaptability enables it to meet various material and processing requirements. Laser processing equipment primarily consists of a laser optical system, control system, and a processing worktable. Laser. The laser is a core component of laser processing equipment, generating a laser beam with specific wavelengths and energy. Common types of lasers include solid-state lasers, gas lasers, and fiber lasers. Each type of laser has distinct characteristics and applicable ranges. For example, solid-state lasers are characterized by high energy and short pulses, making them suitable for drilling and cutting. Gas lasers have a high output power and good beam quality, commonly used for welding and surface treatment. Fiber lasers offer advantages such as high efficiency and long lifespan, and are widely used in the field of metal cutting. 2. Optical system. This is used to focus the laser beam generated by the laser onto the surface of the workpiece and to adjust the direction and shape of the laser beam. The optical system typically includes optical components such as mirrors and lenses. 3. Control system. This is responsible for controlling the output parameters of the laser and the movement of the processing worktable. Through the control system, parameters such as laser power, pulse frequency, and processing speed can be precisely controlled, enabling automated processing. 4. Processing worktable. This is used for mounting and securing the workpiece, as well as for enabling its movement and positioning. The processing worktable can perform 2-dimensional or 3-dimensional movements according to processing requirements to accommodate different shapes and processing needs. 1. Laser cutting. Laser cutting is the most widely used process in laser processing. It can cut various metal and non-metal materials with high speed, good cut quality, and a small heat-affected zone. In fields such as automotive manufacturing and aerospace, laser cutting is used to cut various sheets and tubes to manufacture components. For example, complex shaped parts of a car body can be cut with high precision and quality using laser cutting. 2. Laser welding. Laser welding uses the high energy of the laser to melt and join materials together. Compared to traditional welding methods, laser welding offers advantages such as fast welding speed, high seam strength, and minimal deformation. In industries like electronics and machinery, laser welding is widely used for connecting small parts and precision welding. For example, the welding of mobile phone batteries employs laser welding technology to ensure the quality and reliability of the welds. Laser drilling. Laser drilling can create small holes with a high aspect ratio in various materials. This technology plays a crucial role in the manufacturing of components such as aircraft engine blades and fuel nozzles. It can quickly produce high-quality cooling holes in hard-to-machine materials like high-temperature alloys, enhancing the performance and lifespan of the components. 4. Laser surface treatment. Laser surface treatment includes processes such as laser hardening, laser cladding, and laser alloying. By treating the surface of materials with lasers, the surface properties of the materials, such as hardness, wear resistance, and corrosion resistance, can be improved. Laser surface treatment technology is widely applied in fields like mold manufacturing and mechanical parts repair. For instance, laser hardening of mold surfaces can enhance their hardness and wear resistance, thereby extending the service life of the molds. The development of laser processing technology fully exemplifies the importance of technological innovation. It breaks through the conventional mindset of traditional processing by deeply understanding the physical essence of lasers, leading to the development of a series of processes that traditional methods cannot achieve. This inspires us to dare to break through cognitive limitations and boldly challenge established paradigms in our studies and work. When faced with problems that cannot be solved by traditional methods, we should start from the physical essence to seek new solutions. For example, when dealing with the challenge of processing high-hardness materials, traditional tools may be inadequate, whereas the laser processing technology can easily handle the task. This is a breakthrough brought about by technological innovation. Taking the aerospace field as an example, the blades of an aircraft engine are critical components that must withstand high temperatures, high pressure, and the impact of high-speed airflow. The manufacturing of these blades demands extremely high standards for material and processing precision. Traditional processing methods struggle to create complex cooling holes in high-temperature alloy materials, and they often lack in precision and efficiency. However, by using laser drilling technology, it is possible to quickly produce small cooling holes with a high aspect ratio in high-temperature alloy blades. This method offers high processing precision, meeting the performance requirements of aircraft engine blades. This case fully demonstrates the advantages of laser processing technology in solving traditional processing challenges and highlights the important role of technological innovation in advancing high-end manufacturing industries such as aerospace. In this lesson, we conducted an in-depth study of laser processing technology, focusing on the principles and the equipment of special processing technologies. In Project 2, we learned about the principles of laser processing, which is based on the high energy density characteristic of lasers and achieves material processing through energy conversion. Laser processing is characterized by high energy density, non-contact processing, high processing precision, and great processing flexibility, which have led to its widespread application in many fields. We also introduced the components of laser processing equipment, including the laser, optical system, control system, and the processing workbench. In terms of practical applications, processes such as laser cutting, welding, drilling, and surface treatment play important roles in industries like automotive manufacturing, aerospace, and electronics. Finally, through the integration of ideological and political elements and case analysis, we deeply appreciated the importance of technological innovation. I hope that in your future studies and work, you will be able to break through cognitive limitations and be bold in innovation.